In this question, a 55 kg student is climbing a rope ladder hanging from the helicopter. While climbing, the student leans 0.35 meter backwards from the vertical line of the ladder. So if this is the vertical line here, so he's leaning backwards 0.35 meters. Number one, we need to calculate the torque produced about the top support point of the rope ladder due to the student's weight. So top point pivot is this, and we have to take G as 10 and explain why the ladder starts swinging when the student leans backward and how the student should climb to minimize the swinging. So first thing is to simplify this problem, we have to consider that this entire person's mass or student's mass is acting at a single point, which is center of gravity. So we can deal it as a dot, as a point. Now, this force due to his mass will be acting downwards. If he is 55 kg, so the downward force will be 55 kgf, kilogram force. So that will force will be acting downwards. And now because he's leaning back, so there'll be a difference between the line of the pivot axis of rotation and the COG, the center of gravity of his point. And remember, let's calculate the torque first. So this is the pivot above, and here is the force. So here is the 0.35 meters. So I've simplified it, remove the person, put a point here. So now the 55 kilogram force is acting downwards. So that will be 55 kgf. I can convert into newtons by multiplying it by 10. So because they have asked G is equal to 10, so I've used that. And now see why this distance will be multiplied as calculating torque, because remember torque is force into perpendicular distance between the pivot. So the pivot has this line of action. So the perpendicular distance will be counted from here till here, and that is 0.35 meter. So there will be a torque or movement of force or rotating effect due to this going back or leaning back. So that we can calculate by using this formula. So it comes out to be 192.5 Newton meter. Now there is a movement, right? There is a clockwise movement about this point. So what will happen? This ladder will start swinging due to this movement. So that is why the ladder is starting swinging, because that there is a distance, see, and there is a force acting, and we have a rotational effect, and due to that rotational effect or movement of force, it is trying to swing it. Okay, now how the how the student should climb to minimize the swinging. So see, if we don't want this torque to be acted, we cannot minimize the person's weight. That is there 55 kg he is. We don't want to reduce that, but what we can do it, we can reduce this distance. So as the this will be lesser, the 0.35 will get lesser and lesser. The torque or the rotational effect will also become smaller. So we'll try or tell the student to climb this ladder just very close to this line of action or line of the pivot, so that the distance is minimum. And if it is zero, let's say, then the torque or swinging effect will be zero and the ladder will not swing back and forth. So that is what the answer for these problems are. Let's do the next question. Here is numerical 10. An aluminum rod of length 50 centimeter whose mass per unit length is 0.15 kg per meter is joined with a steel rod of 50 centimeter again, whose mass per unit length is given 0.45 kilogram per meter as shown in figure. So this figure is given to us. At what point should the rod be supported so that it remains equilibrium horizontally? So we should be able to support this rod, entire rod, so that it does not swing or it does not rotate. It remains in equilibrium. So that is a question. So first thing is here direct mass is not given. The mass per unit length is given. So we can calculate, like for example, this side, let's say it's aluminum. So we can calculate this part of aluminum, how much it weighs, how much mass it has. So we can calculate mass of aluminum is 0.15, because see, this is the mass per unit length, and we'll just multiply the length which is given to us, which is half meter. So it will become as 0.075 kg. We'll do the same thing with the steel rod, and it will come as 0.225 kg. So we have calculated the masses, the role of this giving this mass per unit length is over now. Now we have proper masses. But now think about it. If we take only the aluminum part, this left part of the rod, where this all the weight can be considered to act, it can be considered to act at its midpoint. That is called center of gravity. So half of the rod, if we consider on the left, the the entire mass, this mass of aluminum, will be having downward force of 0.075 kilogram force. And same about this mass of steel, it will be happening in between this rod middle point, and that will be 0.225 kilogram force. So now instead of rods, we have like a point object. So one point is here, one point is here, and that is a distance apart of half a meter again. Now think about it. If I put a point here and put a point here, what will be the distance between them? That will be again the zero point 0.5 or half a meter. So with that understanding, let's go forward. So here we are assuming the entire weight of a part of rods can be imagined acting at their midpoint. So these are the midpoints, and the distance between midpoints is again is half a meter. Just take some moment to digest this, that this is the midpoint, this is the midpoint of this, that how much distance it will be in between midpoints. That is again it will be half a meter, because see, midpoint will be 0.25 meter. From here to here it will be 0.25. From here to here will be 0.25. So we consider only from distance from here to here, just need to add 0.25 plus 0.25, again 0.5, zero point 0.5 meter or half a meter. Let's go ahead. So now see this. So this is 0.075 kilogram force of the rod on the left, and this is the 0.225 kilogram force on the right. Right now we want to balance them. So to balance them, let's put a cross and let that distance from this midpoint of the which rod is there, aluminum rod. Let's say it is D. So let's find this distance D. Now, how they will balance? We can apply the principle of moments here, that this force, the moment it will be created around this point, and this force, which will be creating a moment, that moments will cancel out each other. So for this, we can say 0.075 into D, and this for this we can say 0.225 into 0.5 minus D, right? So if this is distance D, complete is 0.5. So this distance, this till here, will be zero point 0.5 minus D. So we just now need to apply math and solve for this D. So this is the calculation part, and then when we solve it, we'll get it 0.375 meters. So that is what we are getting. But the problem is not solved. Let's say what they are asking, what point should the rod be supported so that it will remain in equilibrium? We have found it, it will be from this point, it will be 0.375, like somewhat here, it will be there. But what will be the distance from, let's say, from this end? So for that adjustment, we will do next part. So because we know now from this midpoint, aluminum's midpoint, the distance of where we have to put a pivot or a support here, it will balance, and that is 37.5 centimeter or 0.375 meter. So what will be the distance from here to here? It is midpoint, so it will be 25 centimeter. So remember, it was entirely 50 centimeters, so half midpoint was 25. So this distance has to be added if you want to say from the aluminum end where it is, right? So we will just add it like this: 25 into 37.5, 62.5 centimeter will be the answer. So the rod is to be supported at 62.5 centimeter from the aluminum end of the rod to remain in equilibrium. Now, a little bit here also we can discuss why it has gone this side. If you see the mass, the mass was, this was much more than this much, right? So this was mass was more, this mass was less. So that's why the center of gravity is getting shifted on this side, and that's why we are getting the value like somewhat here.